All right, good afternoon, everybody. I take it everybody has a handout by now. I'm pleased to be here because I was a student of Bill's as an undergraduate here at Western. And while I was an undergraduate, I took one of Bill's famous seminars, which was the gravitation seminar, which I took in 1997, 1998.
So that's the first year we did it.
It's the first year you did it, and even then the book featured prominently in the seminar, so I'm really pleased to hear that the book is very close to being published. All right, so our first speaker this afternoon is George Smith, who's going to talk to us about specific heats.
It's an enormous honor to have been invited here. I'm so flattered to be in the company of the other people. I should have looked back and counted somewhere around 8 or 9 talks I've given in Western Ontario since 1990. And this is the first time I've been invited by anybody but Bill, so you can sort of get a sense of how much Bill has, in effect, tailored my work, directed my work, by constantly asking me to talk about things that I didn't think I was prepared to talk about. Usually wasn't prepared, but somewhere down the road got better. And I'm doing something like that today. This is the first time I have ever done anything in public on this topic, and I chose it rather than talk about Newton, in no small part precisely because I wanted to look at it for years and thought it would be something Bill would like. So, 18 years ago, Bill and I co-authored a paper called Newton's New Way of Inquiry. It spelled out how Newton's approach to marshalling evidence differs from hypothetico-deductive evidence. I read that paper in conjunction with a presentation a few weeks ago, and it made me realize how much a springboard it was for my subsequent work. And maybe Bill would say the same, that paper was a starting point for a lot of things. He and I pursued somewhat divergent paths after that paper. Bill focused on Newton's deduction of his theory of gravity from phenomena and on the evidence coming out of agreeing measurements. I focused on the evidence from 3 centuries of deductions from Newton's theory, continuing to contrast it with hypothetico-deductive evidence, and on other issues about measurement, especially on how physics deals with cases in which different measures of the same quantity do not agree with one another. The last 2 talks I gave here in London, which I think were 4 years ago, at Bill's invitation, were on the first of these topics. Today's is on the second. By the time we were checking the proofs of New Way, Bill and I had both concluded that Newton viewed well-behaved measurement as the ultimate form of evidence in physics. In spite of its emphasis on measurement, our paper nowhere said this, probably because the passages that most support it, like the one quoted here, did not fit easily into our argument. Bill would emphasize the weight Newton puts here on agreeing measurements from pendulums and the eclipses of Jupiter's satellites in support of sidereal time. I emphasize Newton's recognizing that absolute true time is not a pre-existing, ready-made quantity, but instead an abstraction fashioned within physics. The values we assign such abstract quantities involve theoretical presuppositions that are subject to future reconsideration. Those values are obtained from what my colleague Jody Azuni calls proxies, time by the number of arcs described by a certain length pendulum, force by the departure from uniform motion in a straight line, mass by weight, etc. Theoretical principles link such accessible proxies to the less accessible quantities for which they serve as measures. Principles that are again subject to future reconsideration. For just this reason, the question of justifying measurement procedures and the proxies they employ is something physics itself has to concern itself. The way I usually put this is that physics has no choice but to contain its own theory of measurement, adding that Newton seems to have been the first to realize this and recognize its implications. This is not merely because measurement processes themselves are physical. It's because the values assigned to the quantities of physics are mediated by theoretical assumptions and principles. And this raises questions that only physics can answer. Among those questions are the ones listed here. By virtue of what principles does a proxy like the number of beats of a certain length pendulum measure time, and over what range and to what level of accuracy? What do the principles underlying the use of the proxies themselves presuppose, and what evidence is there in support of those assumptions? What exactly is the quantity, like force, as measured by departures from inertial motion, itself a measure of? A question akin to our asking today what IQ or the Richter scale are really measure. Fourth, how should physics respond when two different proxies for the same quantity do not yield the same values for it, like temperature with the expansion of mercury as one proxy, and the pressure measured by the height of a mercury column of the manometer of a constant volume air thermometer as another? I don't know if you realize that. That became the preferred way to measure temperature, by the height, the pressure in the manometer attached to a constant volume air thermometer. Finally, does the physical process employed in measuring the proxy itself introduce systematic errors in the values inferred for the quantity? I think the phrase physics must contain its own theory of measurement is my own, but the idea expressed certainly is not. I started using it 30 years ago and trying to explain to students the fundamental insight driving Pierre Duhem's The Aim and Structure of Physical Theory. Duhem sees the first, second, and fifth of these questions as everyday science, though he would add that the confirmation called for in the second can consist only of agreeing measurements. The third question he would deny has any answer beyond saying that it is an abstract symbolic quantity to which values are provisionally attached in accord with various laws, like the ones governing the thermal expansion of mercury and the increase in pressure at constant volume. And to the fourth, he rejects all talk of the truer temperature or Newton's truer time, insisting that physicists do and only can choose the proxy that makes overall physical theory more simple, more complete, and more exact. To say it more crudely, Duhem pointed to the circularity in measurement being the ultimate source of evidence for physical theory on the one hand, and the simplicity, completeness, and exactness of physical theory being the ultimate source of evidence for its measurements on the other. This led him to conclude that physics can provide nothing more than one among many comparably approximate representations of observed regularities, and to his insistence that the choice of any one representation over others cannot be because it is true and the other is false. I call this view of the knowledge produced by physics, which doesn't differ significantly from Bas van Fransen's, minimal, because I think the reasoning offered by Duhem and his like puts the burden of argument on anyone who is going to claim that the knowledge achieved in physics amounts to anything more than that. Duhem himself was an accomplished thermodynamicist, so a natural place to start trying to meet this burden of argument is with the quantities he most had in mind when he spoke of their being abstract and symbolic, namely energy, entropy, temperature, and in the case of gases, pressure. For hasn't statistical mechanics provided us with answers to what each of these quantities is actually measuring at the molecular level? Answers that, when the microphysics is all worked out, give us a factual basis for saying that the constant volume air thermometer yields values that are more correct than those given by the thermal expansion of mercury. I include E.g. in the third of these because it remained so controversial for decades after Boltzmann proposed it. and in the other two because the answers given by statistical mechanics became more complicated during the 20th century. Duhem did not dismiss statistical mechanics. Indeed, he championed Gibbs's approach on the continent. But he did deny that mean molecular kinetic energy of molecules amounts to anything more than just another abstract symbolic quantity serving to represent exactly the same information as temperature. His reason for denying this, like that of Ernst Mach before him, is that experiments in physics cannot provide sufficient access to the microphysical realm to enable talk of molecules and of the statistical character of thermodynamic quantities to amount to anything more than that. That claim by such figures as Mach and Duhem gave rise to the issue of scientific realism in subsequent philosophy of science, an issue that I confess I have never been able to understand. It also gave rise to issues of reductionism, which I bring up because Bob is here, which I prefer to turn on their head. Instead of asking to what extent statistical mechanics has reduced thermodynamics to microphysics, I prefer to ask, to what extent has statistical mechanics given us experimental access to the realm of molecules? I see the last century and a half of statistical mechanics as offering three things: answers to questions about the status of such macrophysical generalizations as the ideal gas law and the laws of thermodynamics, experimental access to at least some aspects of the microphysical realm, and answers to questions about what such quantities as temperature and entropy are really measurable. The question of how much statistical mechanics has succeeded to these ends is a question about the body of evidence adduced in that century and a half. Again, I didn't come to this view of statistical mechanics on my own. I learned it from teaching an 1875 paper by James Clerk Maxwell. He starts with the wonderfully Newtonian remark that the best theory of the constitution of matter is one that is deduced from macrophysical phenomena. He gives as an example the inference from the phenomenon expressed by Boyle's law to the conclusion that molecules must be moving at speeds exceeding 400 meters per second. He didn't say this as in my edition, faster than a bullet from a handgun. He goes on to explain how Clausius's virial theorem allows the forces among molecules to be inferred from Renault's measured deviations from the ideal gas law. He then turns to the assumption of randomness and the mathematics of statistical distributions that he added to Clausius's kinetic theory. That yielded what he calls, it's on the slide, the greatest difficulty yet encountered by molecular theory, namely the irreconcilability of the values of the ratio of the specific heats of gases entailed by his statistics with Renault's measured value for air. It's striking that in 1875 he called this the greatest difficulty, for in his first paper on the subject in 1860 he had said, and this is a quote, "This result of the dynamical theory overturns the whole hypothesis, however satisfactory the other results may be." They became more satisfactory to him, so he couldn't let it get overturned. It just became the worst difficulty. It was this anomaly that made the ratio of specific heat so important to the history of microphysics, for it did indeed ultimately show, just as Maxwell remarked, quote, that something essential to the complete statement of the physical theory of molecular encounters was not only then, but for several decades thereafter, escaping everyone. Little quick physics, I apologize for this. Gamma, the ratio of specific heats, is defined as the ratio of the amount of heat needed to raise a quantity of gas 1 degree in temperature, holding pressure constant, to the amount needed to raise it 1 degree, holding its volume constant. That is, it's the ratio of two experimentally contrived measures. And so one might well ask whether it itself has any physical significance. It does. In the first years of the 19th century, Gay-Lussac discovered that rapid expansion of a gas, more accurately what we now call adiabatic expansion, follows a different law for boils because a gas cools on rapid expansion and becomes hotter on rapid compression. You should all be happy about that. That's why you have ice. A decade later, Laplace removed the long-standing discrepancy in Newton's theoretically derived value for the speed of sound in air by adding gamma to the equation. Both of these provided direct ways of measuring gamma without having to measure the specific heats at constant pressure and constant volume and then dividing. So by the time of Clausius and Maxwell, the physical significance of gamma was well established. But then, what does gamma measure at the molecular level? On Clausius's original account, some of the energy within a gas takes the form of translational motion of its molecules, and some the form of motion internal to the molecules. Please remember, they had no idea what a molecule was. For him, then, the amount by which gamma exceeds 1 provides an experimental determination to within a multiplicative factor of 2/3 of the fraction of the combined energy that takes the form of translational kinetic energy. Gamma must range from 1 2/3, where all the energy is in translational motion, to a value that approaches 1 as the energy internal to the molecules increasingly dominates. Insofar as gamma, and hence this fraction of the energy, varies from gas to gas, it is telling us something about the capacity of the gas to absorb energy in a form internal to its molecules that does not show up as temperature. When Maxwell added his statistical distribution of the motions to Clausius's formulation in 1860, he derived, under certain assumptions, his equipartition of energy theorem. In the mean, the energy distributes itself equally across all the degrees of freedom of the molecules. Boltzmann subsequently derived this theorem from weaker assumptions and Gibbs from still weaker ones. The equipartition of energy implies that gamma is measuring the number of degrees of freedom of a molecule, and hence something striking about its mechanical structure. Point masses have 3 degrees of freedom, rigid bodies 6, and non-rigid bodies those 6, plus degrees of freedom in which the parts of a molecule vibrate with respect to one another. In short, the equipartition theorem lets us deduce the differing number of degrees of freedom of molecules and gases from the differing values of gamma measured for them. The anomaly in this conclusion came to be characterized in increasingly refined ways over time. This slide's just giving you a distillation of the 4 main things that came to be emphasized. First, since the number of degrees of freedom is an integer, gamma should in principle be confined to certain discrete values. Exactly 1 2/3 with 3 degrees of freedom, 1 2/5 with 5, 1 1/3 with 6, and so on. But the values measured to 4 significant figures did not match these discrete values. Second, while some measured values of gamma fell near to one of these discrete values, others, like Renaud's 1.316 for chlorine, fell in the middle between them. Third, measurements indicated that the values of gamma for at least some gases vary with temperature, but why should the number of degrees of freedom of a molecule do so? Fourth, the characteristic emission and absorption spectra for different gases all contain a large number of discrete lines. While no one was claiming to make any sense of those spectra beyond recognizing that they amount to a fingerprint for different substances, the presumption was that the lines represent different modes of vibration within molecules, and the large number of them indicates that the number of degrees of freedom far exceeded 6, so that gamma should fall much closer to 1 than, for example, Renaud's 1.48 for air. Some encouraging results emerged in the 4 decades between Maxwell's derivation of equipartition and the beginning of the 20th century. In the same year as his dynamical evidence paper, Kuhn and Warburg published a value of 1.67 for mercury vapor, which chemists have said is monatomic. 2 decades later, when Rayleigh and Ramsey isolated argon and helium, They obtained values of 1.659 and 1.652 for gamma, and you can see Ramsey continued with others. So it looked like monatomic molecules really might have exactly 3 degrees of freedom, like a point mass. Similarly, values gathered for such diatomic gases as hydrogen, oxygen, nitrogen, nitric oxide, and hydrochloric acid all clustered around 1.4, suggesting that they all have a dumbbell shape with 5 degrees of freedom, 3 translational and 2 rotational. But then chlorine is a diatomic gas as well, and its most recent measured value fell in the middle between 5 and 6 degrees of freedom. And beyond this were all sorts of polyatomic molecules with values scattered between 1.33 and 1.2. Worse, the variation of gamma with temperature was increasingly being confirmed, and there was still the question of all those spectral lines and why they do not imply many more degrees of freedom. When I first proposed my topic for this occasion, I expected to be entertaining you with the dead-end things people said about the gamma anomaly. Since I've gotten into the subject, I found things much more interesting to talk about. So let me just give a couple of examples of how supporters of equipartition tried to explain away the anomaly. Boltzmann took different stances at different times. In the 1896-98 edition of his book, he raised the possibility that the difficulty lay in the experimental measurements themselves, for maybe gases require times order of magnitudes longer to reach thermal equilibrium than the experiments were allowing. 4 years later, James Jeans, at the time the 22-year-old Isaac Newton student at Cambridge University, I'm always getting it, devised a mathematical theory with totally hypothetical models of molecules to explore the possibility of energy exchange between molecules in the ether as the source of the anomaly in gamma. An especially instructive exchange took place between Lords Rayleigh and Kelvin at the turn of the century. In response to objections that had been raised for years by Kelvin, Rayleigh carefully derived the equipartition theorem from minimal assumptions. He then turned to the question of gamma, ending his article with the anguished remark about needing, quote, some escape from the destructive simplicity of the general conclusion of equipartition, quoted here. Kelvin replied immediately in a famous lecture published the next year, his 19th century clouds over the dynamical theory of heat and light. The first cloud was the Michelson-Morley experiment hanging over the ether, which Kelvin said could be removed by Lorentz and Fitzgerald contraction. The second was the ratio of specific heats. Kelvin ends by quoting the last 2 paragraphs of Rayleigh's paper, and then replying that, quote, the simplest way of arriving at this desired result is to deny the conclusion of equipartition. Duhem, writing his book 2 years later, surely knew Kelvin's reply, if not Rayleigh's article as well. Duhem had more reason to reject the molecular hypothesis than he's usually credited. Understand, however, that Kelvin was not adopting Duhem's position. Kelvin was as much a proponent of molecules as an explanatory hypothesis as anyone was. What Kelvin was saying was that the molecules and the molecular realm are much more complicated than Maxwell-Boltzmann statistical mechanics was allowing for. The issue was not molecules, but the access to them provided by statistical mechanics. To put the point in a way appropriate to the present occasion, the anomaly with gamma was standing in the way of deducing trustworthy conclusions about the molecular realm from observed phenomena. All this began to change, not with Planck's black body radiation paper of 1900, but with Einstein's Planck's theory of radiation and the theory of specific heat 7 years later. In that paper, he offers a Boltzmann-like derivation of Planck's law, and then argues from the analogy that energy must be quantized not just in radiation, but within, quote, molecular kinetic theory, unquote. The specific heats of at least some solids had long been known to deviate from the DeLong-Pettit law at low temperatures. Einstein formed a quantized model in which the molecules forming solids vibrate at a single frequency inferred from their infrared spectrum, and found that it could account for much of the known deviation from DeLong-Pettit. Within the next few years, Joseph Debye, how do you pronounce that? Anybody know? Debye, thank you. Had refined Einstein's model to allow the atom's multiple frequencies of vibration, each with its own characteristic quantized energy. That led to impressive agreement between theory and measurement for a wide range of crystalline solids. This figure's from the mid-1920s, though, not from 1910. Walter Ernst, the driving force behind the first Solvay conference in 1911, hoped the idea of quantizing the energy in gases and the statistical mechanics of their specific heats would be the principal topic under discussion. He did not entirely succeed in this, but it did lead to some papers on the topic. Paul Ehrenfest, like Bohr, had not attended the Solvay conference, but in 1912 had, with his wife, published a major review article on statistical mechanics. In 1913, a few months before Bohr's legendary paper, Ehrenfest put out a theory in which the energy in the rotational motions of diatomic molecules is quantized, proposing that this was the way to finally resolve anomalies in the specific heats of gases. I need to indicate why this proposal makes so much sense. Even before the Bohr model, if the energy entering into any degree of freedom of motion of a molecule is quantized, then a threshold has to be exceeded before energy starts showing up in rotation or vibration. In keeping with Debye, Ehrenfest had the molecules of a gas partitioned by energy level into groups. In the lowest energy group, only translational motion is occurring. But in a higher energy group, the threshold required for energy to enter into rotational motion is exceeded, and the motion involves both translation and rotation. And in a still higher energy group, the threshold for vibrational motion of the nuclei within the molecule is exceeded, and the energy distributes across translational, rotational, and vibrational motion. As the temperature in a gas is increased, the fraction of molecules within the higher energy groups increase, yielding an apparently continuous variation of the specific heats with temperature. In the case of diatomic gases like hydrogen and oxygen, with a ratio of specific heats near 1.4, most of the molecules have energy distributed across 2 rotational as well as 3 translational degrees of freedom. But a few have crossed the threshold for vibration. Chlorine and some other gases, by contrast, have already crossed the vibration threshold at room temperature, which explains why the ratio of their specific heats falls anomalously below 1.4. According to this proposal, the fraction of molecules that are rotating should decrease as the temperature drops. So they had a testable consequence. The ratio of the specific heats of diatomic gases should approach the 1 2/3 value of monatomic gases as the temperature approaches absolute zero. Most diatomic gases liquefy in temperatures too high to test this, but not hydrogen. The data shown are from Arnold Eucken in 1912, working in Nernst's laboratory. Obtaining the value of gamma directly from the speed of sound was not so feasible at very low temperatures, but Eucken did manage to measure the specific heat at constant volume. For an ideal gas, the difference between the 2 specific heats is just the universal gas constant, as up there. The numbers shown for gamma versus temperature are mined from his values in the ideal gas relationship. As you can see, they strongly confirm the testable constants. So one can surmise from them that the rotational motion of hydrogen molecules is indeed freezing out as the temperature gets low. But this is a surmise, a statistical mechanical interpretation of the data. Is there some way to confirm that what is involved here really is the rotation of molecules. Bohr published the 3 parts of his great paper in 1913. It's famous for his model of the atom, but it should be no less famous for finally allowing sense to be made of the complex structure of the spectrum. Line spectra show up when testing dissociated atoms, so-called band spectra when testing molecules. That's actually from hydrogen, from a 1927 paper I'll be talking about in just a minute. With Bohr, the lines in the line spectra came to be seen as transitions of electrons from one discrete energy state to another. So the multiplicity of tightly spaced lines within band spectra must be transitions from one discrete energy state within a molecule to another. That is a transition from one discrete energy state of rotation to another, or a vibration to another. The question was, which molecular transitions are possible and which are not? That is, what are the selection rules for molecular transitions of different sorts? The first 400 pages of Sommerfeld's 1921 book are devoted to the line spectra of atoms, the next 40 pages to the band spectra of molecules. That gives an idea of how much more progress was made with inferring atomic structure from line spectra in the decade following Bohr than was made with band spectra. Lots of effort was going into band spectra, but in the absence of a principled basis for specifying which quantum transitions are possible in the intramolecular forms of energy and which are not, what came to be known as the old quantum mechanics was leaving everyone struggling. Just such a principled basis finally emerged with Heisenberg's 1925 paper, reformulated almost immediately with Born and Jordan as matrix mechanics, and then shortly afterwards with the 1926 wave mechanics of Schrödinger, who, by the way, had been working on specific heaps. The race was on to apply the new quantum mechanics to molecular spectra, with the simplest case of hydrogen the obvious starting point. Working from Heisenberg's mechanics, Friedrich Hund published the 3 parts of his On the Interpretation of Molecular Spectrum, the theoretical basis for molecular orbital theory, in 1927. In it, he concluded that hydrogen molecules have both odd-numbered antisymmetric and even-numbered symmetric states, depending, he said, on the spin of the nuclei. Hund derived an expression for the rotational contribution to the specific heat at constant volume for hydrogen, which he found he could fit very well to the low temperature data by assigning his symmetrical states twice the weight, that is, twice the fraction of the antisymmetrical. That analysis had a moment of inertia for the molecule of 1.54 times 10 to the minus 41st grams per centimeter squared. Let me just pause for a moment there. That's beautiful agreement, and it's totally wrong. Agreeing measures can really be misleading. That's where Phil and I slightly differ. Takeo Hori, carrying out a detailed analysis of the recently resolved ultraviolet band spectra for hydrogen, concluded that the moment of inertia is 4.67 times 10 to the minus 4, 3 times larger than Hund's value. And from line intensities that the transitions between Hund's antisymmetrical states occur about 3 times more often than those between his symmetrical states. That is a weight of 1 to 3 versus Hund's weight of 2 to 1. Hori's numbers, however, plugged into the partition function, yielded a specific heat curve at low temperature, this thing, that not only disagreed with the data, but had a totally different shape with a sharp peak. Which brings me to the centerpiece of my talk, a watershed paper of 1927 by David Dennison. Young Dennison, while a postdoc in Copenhagen and then with Schrödinger in Zurich in 1926, had, like Hund, been among the first to apply Heisenberg's mechanics to the rotation of molecules. Dennison's key proposal in 1927 was that, and I'm quoting, it's up on the board, the time of transition between a state symmetrical in the rotation and an anti-symmetrical state is very long compared to the time in which the observations of specific heat are made. In effect, then, the gas at low temperature is composed of two different gases. Parahydrogen, which Hund had treated as symmetric, and orthohydrogen. Each of these individually reaches thermal equilibrium rapidly, but the overall gas reaches thermal equilibrium very slowly. It's about a matter of a month or two for it to reach. Denison proceeded to derive the rotational specific heats of the two kinds of hydrogen and let the low temperature measurements reveal that the ratio of antisymmetrical to symmetrical rotating molecules is close to 3:1. In his table, the independent variable sigma is the rotational wave number. The experimental value of temperature is the temperature at which the combined rotational specific heat matches the measured value. And the calculated temperature is derived from sigma, so that the column between them should be a constant. The average value of sigma times the temperature is 85.5, implying a moment of inertia of 4.64 times 10 to the minus 41st, in close agreement with Horry's value derived from the spectrum. In a note added while the paper was in press, Denison pointed out that the 3:1 ratio in room temperature should be expected from the Schrodinger wave equation if the nuclear proton spin has the same value of plus or minus 1/2 proposed for the electron, which, by the way, flips which states are symmetric and antisymmetric in the wave equation. Denison's proposal that the measurements were not being made for a gas at equilibrium, but instead one in a metastable state requiring a long time to reach equilibrium, was confirmed in two ways over the next couple of years. Eugen extended the time measurement at low temperature, and Bonhoeffer and Hartek found charcoal to be a catalyst that promoted rapid exchange between symmetric and antisymmetric forms of hydrogen. In both cases, the confirming experiments got measured values in agreement with the calculated high peak curve in the figure. Notice what Denison's insight amounted to in terms of measurement. They had thought that the low temperature experimental specific heat curve was measuring the rate at which rotational motion was freezing out as the temperature dropped. Instead, it was measuring the relative fraction of two distinct gases that have very different capacities to absorb energy in rotation. So how can I say a 4-page article in which the main step amounted to little more than a curve fit was a watershed? For one thing, after 65 years in which the discrepancies between theory and measurement of specific heats raised questions about what was wrong with the theory, Denison, in the words of Newton's fourth rule of reasoning, was taking the new quantum theory to be exactly or very nearly true and asking what the discrepancies were telling us about the world. Asking this led for the first time to mutually corroborate, hear that, mutually corroborated answers to the question of what's the key observed quantities are measured, the band spectra and the low temperature specific heats in their ratio. The lines of the band spectra are measuring the energy needed for transition from one state of rotation of a hydrogen molecule to another, including the threshold quantity of energy for rotation to occur at all. Their intensities are measuring comparative numbers of transitions, and the spacing between them provide a measure of the moment of inertia and hence the distance between the nuclei of the molecule. The specific heat at reduced temperatures is in effect measuring the fraction of the molecules in which energy is distributed across rotational as well as translational degrees of freedom. Gamma, therefore, does not provide a straightforward measure of the numbers of degrees of freedom, as Maxwell had hoped, but it can be used to confirm inferences about degrees of freedom obtained from the spectrum. Finally, Denison's paper identified a source of systematic error in the specific heat measurements when taken to be for a gas in full thermodynamic equilibrium, leading to reconsideration of how such measurements need to be made. What we are looking at here illustrates what I mean when I say that physics has no choice but to supply its own theory of measurement. Further grounds for Denison's paper being a watershed comes from research done in its aftermath. Ralph Fowler, who had communicated Denison's paper to the Royal Society, asked one of his Trinity College proteges, W.H. McCrae, to recalculate the specific heats of hydrogen at higher temperatures, where vibrational degrees of freedom come into play, from Horry's empirical values from the energy quantum. The ortho-para distinction ceases to matter much at higher temperature, but the higher the temperature, the greater the displacements of the two nuclei in vibration, and hence the less the vibration takes the form of a simple harmonic oscillator. The good agreement McCrae found at high temperatures was especially impressive because it confirmed the non-constant spring between the nuclei inferred from Horry's analysis of the band spectrum. In his 1933 Silliman Lectures on Hydrogen at Yale, Owen Richardson remarked that its band spectra had provided the most stringent test of the new quantum mechanics. I don't know enough yet to confirm that, but hydrogen, even with the notable discrepancy you see here at 1,000 degrees, was supplying important evidence. McCrae noted at the end of his 1928 paper that his analysis for hydrogen at higher temperature yielded, quote, altogether wrong specific heat curves when applied to oxygen. Its rotational states would already be in play at 30 degrees Kelvin if it did not liquefy at a much higher temperature than that. So the issue with oxygen and with nitrogen too is the high temperature variation of the specific heats. Two advances in the early 1930s were needed to match values calculated from spectra with the measured specific heats of oxygen. First, Henry and his colleagues devised a refined method of measurement that provided more time for the gas to reach thermal equilibrium. The systematic error in all prior measurements came from the slow exchange of energy from rotation into vibration. Then Bernard Lewis and Gunther von Elbe, 20 years later, engineering mentors of mine, I'm proud to say, proposed an electronic state that had not yet been observed in the spectrum for oxygen to account for the very high temperature discrepancies. Gerhard Hertzberg subsequently verified this state spectroscopically. Notice here that the discrepancies were all due to systematic errors in measurement at moderate temperatures from a metastable quasi-equilibrium and at high temperatures because the electronic spectrum had not been fully resolved. Theory taken to be exactly or near enough true was serving to disclose these errors. Deuterium, the atomic mass 2 isotope of hydrogen, was discovered from its spectrum by Harold Urey in 1931. It provided further confirmation of the very slow exchange of energy between ortho and para-hydrogen at low temperatures. A molecule consisting of hydrogen and a deuterium nucleus, HD in the slide, is not symmetric to begin with, and hence doesn't raise statistical counting issues between symmetrical and antisymmetrical molecules. Clusius and Bartholomew confirmed good agreement between calculated and measured values of the specific heats of HD gas in 1934, and then that same year for deuterium gas as well. A pure deuterium molecule does raise counting issues between symmetric and antisymmetric forms, but now the 1/2 nuclear spin has to be doubled. Both theory and the spectra indicate that at room temperature there are twice as many orthohydrogen molecules, in this case with even numbered states, as para-hydrogen, in contrast to the 3 times for simple hydrogen and the shapes of the theoretical specific heat curves, quite different for them than for simple hydrogen. Once again, however, treating the gas as consisting of a mixture of 2 different gases produced a calculated curve that matched experiment, and measurements made in the presence of the charcoal catalyst agreed with the calculated thermal equilibrium point. Denison's proposal turned out to be robust. I could go on to other diatomic molecules, but let me limit myself to chlorine, my example of an anomalous ratio of specific heats at room temperature. The reason, of course, is that the greater masses of chlorine nuclei bring the threshold of vibration down low enough that they are already vibrating as well as rotating at room temperature. As the figure shows, the anomaly of chlorine disappeared with the new quantum theory, providing a basis for interpreting the spectrum and partition functions, replacing partition functions, replacing equipartition of energy within statistical mechanics. This was not just a further successful test of quantum theory. Things were being learned about chlorine and other diatomic molecules. By the mid-1930s, research was shifting from diatomic to the more challenging problem of polyatomic molecules, for which the chemist E. Bright Wilson contributed much of the theory. Denison himself started working on the polyatomic in 1931, focusing initially on carbon dioxide. It's the sole example I'm going to offer here of the agreement achieved between calculated and measured specific heats for a polyatomic gas. The capacity of carbon dioxide to absorb infrared radiation in its vibrational degrees of freedom is why it's a greenhouse gas. The figures from 1934. The work achieving it established that carbon dioxide has only 2 degrees of freedom in rotation, and hence it's a linear molecule with the 2 oxygen nuclei lining up on opposite sides of the carbon nucleus. That illustrates how much structural information can be obtained from the spectrum using such quantities as specific heats for corroboration. The evidential reasoning followed the same path in all this research. It starts from the band spectrum as resolved so far. The new quantum mechanics is taken to be exactly true throughout, but even for a diatomic molecule, the Schrödinger equation or its Heisenberg counterpart cannot be solved exactly. So the interpretation of the spectra initially idealizes the molecule as a rigid rotor in rotation and a harmonic oscillator in vibration. Later, as the spectra or the measured specific heats demand, perturbation methods are used to add the effects of the centrifugal expansion of the distance between the nuclei in rotation. As it rotates faster, they spread apart. The variability of the spring joining them, producing anharmonic vibration and interaction between rotation and vibration. As with orbital research based on Newtonian gravity, the robustness of such refinements is a source for the most compelling evidence that what is occurring really does involve mechanical rotation and vibration. The equations derived from quantum mechanics for the model of the molecule relate the spectral lines and the distances between them to quanta of energy and such features of the molecule as its moment of inertia, entailing a spacing between nuclei, and its natural frequencies in vibration, entailing a strength of the spring. These are incorporated into a partition function, employing quantum counting for the molecule as modeled, from which such thermodynamic quantities as specific heats and entropy can be derived as functions of temperature. If comparison of the calculated specific heats with measured values shows discrepancies, the various elements entering the calculation, the spectrum, the model employed in its quantum mechanical interpretation, and the partition function are revisited, along with the possibility of systematic errors in the measured value. Throughout the process, the new quantum mechanics and the replacement of equipartition of energy by a partition function remain fixed as background generic theories. The process uses these theories to derive features of molecular structure and motion from one set of measurements, the spectrum, that are then confirmed by another set of specific heats. All this in a sequence of successive approximations, with the background theory serving to distinguish inaccuracies arising from idealizations and approximations from other contributors to any residual discrepancies. What's difficult to convey is the scope of the research that was carried out this way. There are a lot of diatomic and comparatively simple polyatomic molecules for which the structure and motions can be determined. The slide lists books that came out of the research over the first decade and a half after Denison's paper. I single out Hertzberg, not merely because his volumes became the compendium of the research, but also because he, like Bill, was an academic immigrant to Canada. He was, in fact, as many of you may know, the first Canadian ever to get a Nobel Prize in the physical sciences. The 1939 first edition of Hertzberg's diatomic molecule volume references 734 articles, almost all of them post-Denison. In the final printing of the 1950 edition, the number had grown to 1,611 articles. Table 39 at its end, which runs 79 pages, lists structural properties for more than 250 distinct diatomic molecules. Historical narrative always risks putting events in sharper relief than they actually were. So you can legitimately ask whether I haven't made Denison's paper more of a watershed than it actually was. I think I can defend my claim, which I am by no means alone in making, but it's less important to me here than the contrast between the kind of science before and after Denison. For more than a half-century, researchers had struggled to make sense of both the spectra and the specific heats. After 1930, they came to be engaged in sustained, data-driven science. 3 years ago, I gave a series of lectures at Stanford on the role of theory in science, the last one on seismological research into the deep structure of the Earth. One of Stanford's seismologists remarked to me afterwards that before my lecture, he had always thought of his field as data-driven. I replied that that was my whole point. Continuum mechanical theory had put seismologists in a position in which they could conduct data-driven science. That's my point here. Denison's paper and its corroboration over the next 2 years showed that the new quantum mechanics and quantum statistical thermodynamics could serve as a basis for data-driven research into the structure and motion of diatomic and at least some polyatomic molecules. Just as the theory behind seismology had allowed researchers to gain empirical access to the deep structure of the Earth, the advances in the late 1920s allowed researchers to gain not just access, but verifiable access to details of molecular structure and motion. Calling it data-driven does not mean that just anybody could do the research. Details of molecular structure did not fall into place immediately upon the advent of the new quantum theory, any more than the details of orbital motion had fallen into place as soon as Newton announced his theory of gravity. Resolving band spectra, extracting rotational and vibrational constants from them, devising approximate solutions to quantum mechanical equations, constructing partition functions, and refining methods of measuring specific heats was challenging work that highly talented scientists could find absorbing, in many cases, for their whole careers. Such challenges are just what Tom Kuhn said drives those engaged in normal science. It was normal Kuhnian science in other ways too. It was research spread across an international community of individuals bound together by what Kuhn would have said was an exceptionally clear example of a paradigm before he decided to abandon the work. Indeed, it was the very paradigm in which Kuhn himself was trained at Harvard by John Van Vleck, one of the principals of the field of research I'm talking about, who subsequently focused more on the molecular basis of magnetic susceptibility. Like most data-driven science, the research on molecular structure and motion was not likely to produce Nobel Prize-winning discoveries. While a handful of the few hundred people publishing in the field did receive Nobel Prizes, Hertzberg in chemistry in 1971, in effect as a Lifetime Achievement Award, and Van Vleck in physics in 1977 for his work on magnetic susceptibility, the best I can tell, none of the individual findings about molecular structure and motion in the 1,600 papers Hertzberg listed on diatomic molecules and the nearly 1,000 on polyatomic was ever singled out for a Nobel Prize. Those engaged in the research seem instead to have been inspired by the thought that they were establishing facts once and for all about molecules. That points to a respect in which Kuhn's description of normal science does not fit. He said, quote, "Mopping up operations are what engage most scientists through their careers." But calling the efforts of those working on molecular structure and motion in the 1930s and 40s mopping up operations grossly understates the value of what they accomplished. Consider the huge number of details they established about molecules and their motions. For example, the equilibrium distances between nuclei in scores of molecules and the comparative fractions of energy in the form of rotation versus vibration and translational motion in different gases at different temperatures. Associated with each of these details are counterfactuals announcing how the spectra or thermodynamic properties would be different if the detail in question were different. Beyond those are details and counterfactuals concerning test procedures employed in measuring specific heats and resolving spectra. All those details and the counterfactuals associated with them had at least as much claim to being knowledge as the quantum mechanical theory involved in their discovery. Indeed, in at least one respect, they had more claim to being knowledge. For Dirac had shown by 1930 that the non-relativistic quantum mechanics of Heisenberg and Schrödinger was by no means going to be the final word. Yet there was no reason to think that such details as the equilibrium distances between nuclei to the level of precision that was then being quoted were going to change in the future. Questions about the nature, scope, and limits of the knowledge gained by the sciences are central to philosophy of science. The myriads of difference-making details established with the aid of theory comprise by far the largest fraction of anything that can legitimately be called knowledge achieved in the sciences. Yet they rarely get much attention in the philosophy of science. Understand, I'm not saying that every detail pinned down in the research of molecular structure had equal claim to being knowledge. Already in 1930, Hertzberg remarked that calculated values of specific heats, quote, can be trusted to such an extent that further direct measurements, which are difficult, particularly at high temperatures, are hardly necessary for diatomic molecules. That makes me wonder whether people quit taking the trouble to check calculated thermodynamic values against measured values as the research matured. Even when they did, questions about the precision with which calculated and measured values agreed have to be asked. More important still is whether robust sources for small discrepancies between calculation and measurement were pursued in fact. Questions like these can be answered only by going through the literature molecule by molecule, critically assessing the evidence in the manner of someone writing a review article. The same has to be said for the question of how stringently any molecule tested non-relativistic quantum theory. Every molecule whose features were adduced from spectra tested quantum theory to some extent, for even success in accommodating data is a weak test of theory. The interesting question is how stringently quantum mechanics was tested en passant, as it were, in this research. The answer to that is surely going to vary from one molecule to another, and hence again can be answered only by going through the literature molecule by molecule, a process I have very barely begun. The transitions in the history of science that Kuhn stressed involve discontinuous changes in the way we conceptualize the world. I've spent my career in philosophy of science looking at transitions in which areas of research have gone from not being able to turn data into evidence at all effectively to being able to do so with extraordinary success. In the transition at hand, the data were the band spectrum and the specific heats of gases and their ratio. The question is what made this transition possible? Part of the answer, it goes without saying, was the new quantum mechanics and the related quantum counting and the partition functions of statistical thermodynamics. But these are generic theories that did not by themselves yield any specifics about individual molecules, any more than Newton's law of gravity yielded any specifics by itself concerning motions of the planets. The transition to data-driven science involved three further elements beyond generic theory. First, corroborated answers were needed to the questions of what such observable quantities as the ratio of specific heats and the spacing between lines in band spectra really measure. Answers that fully complemented the answers to the corresponding questions about such thermodynamic quantities as temperature and entropy and the line spectrum. Second, specific, projectable, even if approximate relationships, Bill would call them systematic dependencies, had to be confirmed between those observables and various microphysical quantities in order for inferences to be drawn from one to the other. These relationships, not generic quantum theory itself, provide the basis for counterfactuals. And third, systematic errors in the procedures that were being used in measurement had to be identified, leading to new procedures, especially for determining specific heats over temperature ranges in which degrees of freedom were either coming into play or freezing out. In other words, discoveries had to be made about what was actually being measured versus what they all along thought was being measured. Not just the last of these, but the three together cover the elements I listed at the outset as comprising a theory of measurement in physics. All of which brings me to three small gifts for Bill on this occasion. First, data-driven science was what Newton was striving for when he took his laws of motion to be exactly or very nearly true in order to derive his theory of gravity from phenomena. Second, there's a parallel between the developments in the late 1920s centered on Denison's paper and developments involving the theory of gravity in 1749. In that year, D'Alembert obtained the first confirmed value for the magnitude of the force of the moon on the Earth, claiming in conjunction with it that for the first time evidence had established the interaction of celestial bodies. In the same year, Clairaut removed the factor of two discrepancy between the calculated and observed mean rate of precession of the lunar apogee, which Curtis spoke of earlier, finally establishing the reliability of the rate of precession as a measure of the exponent of distance for the centripetal force of motion in the orbit. Euler called this, not Newton's law of gravity, this, quote, the greatest discovery in the theory of astronomy, without which it would be absolutely impossible ever to succeed in knowing the perturbations that the planets cause in each other's motion. Third, the gift I think Bill will most enjoy, central to the developments of both 1749 and the late 1920s, were agreeing mechanisms. Bill, have a wonderful time. Sorry to read that to you, but if I hadn't read it, I'd be here for 2 hours.
All right, so we have about 10 minutes for questions now, and then more time later. Brian.
I just want to say, wow.
I'm just beginning this research, and I'm sure there are lots of mistakes. Go ahead.
I just noticed that the list of people working on the new theory of molecular structure that you put out, the books, it seemed conspicuously missing the book by Wigner, Group Theory of its Application to Quantum.
It's later.
Oh, it's later. Well, no, it's 1930.
Oh, no, well, that was just on really,
31.
That's dealing with line spectrum.
Yes, exactly, yeah.
And that's why it's not.
Okay, so you do take this to be a different
I
program of
can tell
research.
the
I was
whole
wondering
story.
if it's...
When Hertzberg submitted his manuscript, one of the two reviewers rejected it, saying it doesn't have anything on group theory. His letter in reply was, this is about molecular spectrum intended for the general audience, not for the specialist whom I know wrote that review. The book was published without the group theory. But that's, I mean, let me just say what I've done. I didn't go from the theory. I almost never go from theory when I do research. I go from the evidence and go back to the theory. Wigner disappears in the molecular research until in the late 40s and early 50s. And that's the sole reason for it.
Yeah, he seems to be to not fit this mold that you're describing.
But you know, I'm trying to indicate what I really wanted to push is get a successful theory of measurement and the whole way you do science changes. And that this is an example of that, and really what happened with Clairaut and D'Alembert is another. So that's another reason for not trying to cover everybody. There's a very, very good paper out now, Clayton Gerhardt, thank you, covering the history from 1911 up to the Denison paper, really in detail. He brings everything to some extent. That was not my aim. I wanted to get to the later part.
Rob.
What way do you think that the azotic hypothesis essentially is providing a strong indication for the success of these phenomena, including the basic theoretical idea of liquid particles?
I don't know enough to answer that question. The place I would turn is the Ehrenfest paper, among others, but I just don't know enough statistical mechanics yet to say. What I jumped on, and I said it just in passing, what's the evidence it's really mechanical rotation and vibration? Let me explain that. Just take harmonic oscillator. Any number of things beside mechanical systems can fit a harmonic oscillator. It doesn't tell you it's mechanical at all. But now add the following complexity. It's rotating. As a result, centrifugal force is separating the nuclei, and therefore the vibration frequencies are changing in the process. Okay? It ends up, you have three different ways of measuring that spring constant, which is not a constant between two nuclei, and they all converge, one from rotation, one from vibration, and one from electronic structure. That's the evidence through the anharmonic vibration, the centrifugal separation, etc. That's what's showing it's not just an analogy, it's really a mechanical system. Now I'm not saying really here quite the way Dugan would want me to, but it's the evidence that's strongest that what we're dealing with is a mechanical system. Right.
On one of your slides, you had Hund's calculated curve and the data that seemed to fit it very nicely, and you remarked it looks really good, but it's wrong. Could you just elaborate on that? What was wrong with it, and why did the agreement seem so good? It was spurious.
Well, the agreement seemed so good because he curved it.
Okay.
He made twice the symmetry to the anti-symmetry precisely to get that curve.
Okay.
That's how he got the curve. He did not have, I have to go into a little technical detail. Homopolar molecules do not have they do not show up in the infrared region because they can't absorb light in any straightforward manner. As a result, Hund had no band spectra from which he could draw useful inferences for hydrogen. He had one for nitrogen. Hori, working in fact in Copenhagen, a Japanese chap working in Copenhagen, picked up the ultraviolet band spectra that others had just discovered, and he used it. Hund didn't have it. So, you know, both Hund and Denison were curve fitting, openly curve fitting to fit the data. But the difference is Denison had seen Hori's results and had good reason to think you could not trust. You really needed the spectrum of hydrogen to do this properly. That's the best way to say it. Does that answer your question, Adam? I mean, the paper just referred to goes into much, much more detail about this than I have. But it's a complicated story. New data emerged. Molecules that don't have electric dipoles can't absorb light in any straightforward way, so you have to deal with them differently. And that's what Hori, in effect, found a way to deal with hydrogen.
Al.
Okay. I noticed you mentioned residual, inferring things about the world from residual discrepancies. And that reminds me of, and actually some of the thrust of the paper reminds me of Herschel's, the younger Herschel, book on method where he discusses the method of residual phenomena as one of the many, many methods of science he discusses. Have you ever read about that or thought about that in terms of your own perspective on
No, it's
science?
a great suggestion. Yeah. I mean, I've come to believe that the highest quality evidence in science almost all the time comes from discrepancies between idealized theory and observation that you then discover the source of, and that becomes a finer and finer process. So I was surprised when that worked out here. I didn't know that's what was going to emerge here, but I'm quite pleased it did. But no, I love the diversion. I mean, I have the book, but at some point when I was 50 years younger, I must have read it. And that's about right, 50 years younger. It was when I was an undergraduate.
He says it's in the advanced sciences, it's most commonly used. Advanced.
Well, it was already taking place in celestial mechanics, so why shouldn't we?
I just wanted to say, in thinking of how to explain my question this morning, I wrote down secondary phenomena. Thinking of some of the things you talked about, like I think,
That's a technical term I've started using for
Yeah.
10 years.
yeah, that's what I was thinking
It's
about.
not observable and always presupposes, it's always a difference between a theory and observation. Go ahead.
Yeah, no, I was just thinking that there's a kind of view fertility in structuring theories in such a way that you can use them in order to get secondary phenomena and build a theory of measurement from a theory itself.
Well, I think it's more than utility, and let me just say why. It goes back to Curtis's paper this morning. He didn't quite have time to tell you about the Spencer-Jones great empirical term, the Hill-Brown theory. But let me present it to you the way I present it all the time. Hill-Brown theory might have worked. That's the way I was taught when I was an undergraduate by Brower. It was fine. I didn't know there was a grand empirical term in it until I started reading. If it had, you would have the following ambiguity. A large amount of least squares goes into any celestial mechanical theory. Here you have a very good fit. How much of it is due to statistical fitting? How much of it is due to the fact that you have physically the right theory? Now, take the 1,405 terms of Hill-Brown theory, put them all together, and have something come out with a really clear signature. Develop evidence that's definitely a fluctuation in the rotation of the Earth. Confirm that with lasers on the moon, reflecting lasers on the moon, etc. And what have you said? Not only is this fluctuation in rotation physically real, but the 1,405 terms must be physically real too, because they're giving rise to a very small discrepancy, smaller than any of them, that's physically real. So I see discrepancies as the principal source that something is physical rather than mere curve-fit representation. That's the essence of the message in all my work the last few years. And as I say, I don't know how true it is in this case, because I got to go read. I'm not going to read 2,600 pages of papers, but I'm going to read enough of them that I can write a review on it. And I don't know what I'm going to find. I don't know how much people said, this agrees with quantum theory, let's not push the issue. As you saw, there were a lot of discrepancies in those curves I showed. That's why I showed them. They're not perfect fits. And I don't know the follow. I can't find, even in 1970, what happened to that discrepancy in hydrogen at 1,000 degrees. It's still being quoted by Guggenheim as of 1970, still being shown in this book. And I don't understand.
All right, let's thank George again.